So this video is about the sine rule or the law of sines, and I just wanted to do a quick demonstration here of what's going on exactly with the sine rule or the law of sines. So this is not a proof of why the sine rule works. It's just a little visual numerical demonstration here to show you what's going on here. So I have a triangle here, three angles, capital A, B, and C, and side lengths A, B, and C, lowercase. Okay, and I've created a triangle here, and I'm just going to zoom, or not zoom, but kind of move the triangle around. And now I know there's a lot going on here with these numbers that are changing, but again, it's just to see that the ratios are always the same. So the sine of angle A divided by A. Well, in this case, angle A is 44 degrees, and the side length of A is 11.2. What is the sine of 44 degrees? I don't know and I don't care. It's a decimal, right? Divided by 11.2. What is that number? I don't know and I don't care because the computer's already figured it out for me there, okay? So whatever the sine of 44 degrees is divided by 11.2, it's a number. In this case, 0.06194 rounded to 5 decimals, okay? For example, sine of B. For angle B here, that is 53.1 degrees. And the side opposite angle B is 12.9. What is the sine of 53.1 degrees? I don't know and I don't care. It's a decimal, right? Between 0 and 1. When I divide that by 12.9, I get another number, 0.06194, rounded to 5 decimals. And we can see that those ratios are the same, and that's exactly what the law of sines or the sine rule tells us. These ratios, the sine of an angle divided by its opposite side, are always going to be proportional to one another. They're always going to be, well, I shouldn't say proportional, but equal to one another. All right? And we can see as I change the triangle, angle A, so as I slide this vertex of the triangle around, just focus on A and B. Angle A is changing, isn't it? Look at angle A. Angle A is really big. Now it's really small. Okay? The side length, side A, that stays the same. As this angle changes, I can see it up here in blue, the angle is changing, so the sine of the angle is changing. But the side length is staying fixed. It's staying put at 11.2. That doesn't change. I can see that geometrically, just as I move this around. The side length isn't changing, but the angle certainly is. Okay? If I keep moving vertex A, I'm also noticing some changes in B. Of course, angle B is not changing. Angle B is staying fixed. That's not moving like angle A is. But as I change angle A, side length B changes. Side length B is much shorter here. Over here, it's much longer. So as I slide this vertex around and I change the shape of the triangle, I'm changing two things here if I just focus on A and B. Okay? I'm changing angle A, and I'm also changing side length B. And I can see those are the two that are changing up here in the blue text and the green text. Angle A is changing and side length B is changing, okay? However, what's important to note is those ratios, yeah, the ratios are changing, but they're changing at this, consistently with one another. They're always going to be equal. Okay? So when I have this triangle, for example, the ratio of the sine of angle A to side length A is 0.8265. If I change it over here, it's 0.0513. Okay? But as it changes, that proportion for angle B and side length B, yeah, the side length B changes, but it doesn't change the overall fraction. That doesn't change the ratio. Those two ratios are always going to be the same no matter what I do with this triangle. And that's what the sine rule tells us. Again, this is not a proof of why this works. It's just a little visual representation to see what's going on. Okay. And lastly here, you can see with angle C here, if you want to take into account angle C, as I'll just keep changing this vertex of the triangle. I'll keep sliding this around. Now, when I do this, both things are changing for C, right? Angle C is changing, And side length C is changing as well. Both of those are changing. However, when they change, the fraction changes, but all three of these fractions, all three of these ratios stay the same throughout the triangle. And that's what the sine law tells us, or the sine rule. All right. Hopefully that makes a little bit more sense. And what if I mess around with B here? I can change angle B. I can change angle C. I can move this up, I can move it down. Notice those ratios are all the same. That's what the sine rule tells us. So I don't care what the sine of 78.7 degrees is. When I divide it by its opposite side length, that value is going to be the same if I look at angle A or if I look at angle C. So hopefully that makes a little bit more sense.